Hello, my name is Clark Newman. I will be doing a quick presentation on the focus on navigation performance of a near Perilune in a near rectilinear halo orbit for a crewed station. And today I'm going to focus mostly on how FreeFlyer was used to achieve or to execute this analysis. So, moving on. Um, For this analysis, we're looking at the Gateway mission, which will be in the NRHO around the moon. So you can see my cursor here. It's a 6.5 day period where we're mostly in low velocity, long periods of low relative velocity near Apolloon, punctuated by short, high velocity, high sensitivity passes near Perilune. And so the way this orbit determination process works is that we track the gateway with Deep Space Network, take that tracking data down, process it, and then send back up a processed state estimate, which is used on board to execute activities and events. So what we're looking at is in that time between taking down the data, processing it, coming up with commands, and re-uploading it, we have predicted over time where Gateway will go, and it will actually be that state that we upload at the right time to the Gateway. So when we are doing predictions through Perilune, we go through this period where we have this high sensitivity high velocity sensitivities in this dynamic region, so that the errors can spike in the vicinity of Perilune. So in this plot right here, we have the time spent under 10,000 kilometers, comparisons of estimated spacecraft propagating through Perilune against our Truth spacecraft. And you can see that the velocity errors spike in the vicinity and then kind of come down to slightly elevated values. So as you predict through multiple Perilunes, your errors kind of grow in a stepwise mode fashion through multiple revs. So the propagations from a tracking data span through or through Perilune is kind of what we're looking at for both the way that we are doing orbit determination and the propagations through that dynamic region. So the way we set up the problem is that we have our reference spacecraft on an ephemeris that is phased to avoid any eclipse. We also have our Truth spacecraft, which is perturbed from our reference and numerically integrated and tracked with the tracking data from the Deep Space Network. And then finally, the tracking data is processed on an estimated spacecraft, which is again perturbed from our Truth spacecraft and also given a covariance or kind of confidence of the navigation solution. And that's kind of shown by this width of the shaded area here that we call sigma naught. So we predict over some time span until we receive tracking data. We filter that data over time until the end of the tracking data span. And then from there, we produce predictions into the future. And we can kind of say that Perilune is somewhere over here. And you see that there's multiple predictions coming off of a single solution, and that accounts for when we're crewed, we have random desaturations, which we create multiple predictions from a single solution, so that each one gets random perturbations to create a proper variance of predictions from a single solution. So the way it works in the NRHO when we're uncrewed is that we have 3 8-hour DSN passes per rev. And we've labeled them number 1 right here, which is sets us up for orbit maintenance maneuver at true anomaly 200. Then we have a pre-Perilune pass, which one of the analyses we look at is shifting the location of this pass specifically. And then, of course, we are looking at the prediction from that pass to Perilune. And then after Perilune, we have a DSN pass, which can help rectify any errors that we've picked up from this Perilune pass. And then the whole cycle repeats for every NRHO and at about a 6.5 day period. And the big difference when we are crewed is that we will be tracked continuously, but there will still be this prediction here from a data cutoff, or when we stop taking data, process that data, and then upload a state that may be in the vicinity of Perilune, or will include a prediction around Perilune. So changing gears and talking about FreeFlyer a little bit, how we used FreeFlyer to do this. The DSN tracking is simulated and processed by FreeFlyer in a single execution. And so what we see right here are the spans in green where DSN is tracking, I guess, geometrically, or the geometry of the NRHO. We've got 8 hours on the outbound, 8 hours near Perilune, and then 8 hours on the inbound leg. And then our predictions to Perilune and through Perilune. So we track data, but the tracking data is executed with the Truth spacecraft. The orbit maintenance maneuvers are executed on the Truth spacecraft and estimated spacecraft. They are targeted with the estimated spacecraft. And that is all works together in a Monte Carlo analysis to produce the solutions and data we're going to look at. Alternatively, you can do a covariance or consider analysis. That can be done with a single spacecraft. Since you're not actually updating its state, you can just look at the evolution of the covariance over time. That helps you kind of more for feasibility and at the beginning of your analysis before you start to get more detailed. That requires Monte Carlo analysis. So the simulation that whose screenshot you just saw here. The inputs for that are our Truth ephemeris, that phased NRHO that avoids eclipses. We also have a mission file that we're going to talk about. It's a text-based abstraction of simulation commands that tell FreeFlyer what to do, and we'll talk about that more in the next slide. We also have a slate of configuration files, such as property files, an output file, a filter tuning file, a data plan file, and event files. And so these guys define all the things that go into the simulation to set up the physical properties, initial uncertainties, what output you want to get, what kind of analyses are run in the middle of this guide. That includes predictions. You'll see those, the results of those later on. We also have the filter tunings in a separate file. The data plan that defines those 3 passes, or when we're crude constant, and then anything that that would perturb the gateway or change its configuration can be put into an event file. And then all of these guys are then kind of wrapped up in a UI file, meaning user interface, that use a user interface to choose all these guys. And then once you choose those guys, all your selections are dumped into a UI file, which is then saved to the output directory so that you can just grab that and reproduce anything without having to remember or save off your specific settings. So it kind of simplifies reproduction or saving a specific set of inputs to share to another analyst. So talking about those mission files real quick, it's a higher level abstraction of the simulation commands. I mentioned that. So it is a text file that has commands in it in a easier to read fashion. So these commands are kind of tell the filter, tell the simulation what to do. And so this is a kind of example mission here that starts at the Apolloon, filters for 1 full NRHO revolution, then goes to Perilune, then goes for 1.3 days, and then executes an event file that has this definition of this docking event, where it contains the perturbation and then the configuration files that you are changing to. So it would then change the mass if any crew have joined, and then if that changes, in turn changes the data plan. So then this kind of happens some more. We do some more filtering, another configuration change, some more filtering, and then that's the end of the mission. And then for a Monte Carlo, of so many iterations, that would be so many runs through this actual file. And the reason this was made is the fact that the Gateway mission has a long, complex, and evolving timeline of activities, of configuration changes, and we didn't want to have to make code changes for all of this stuff that keeps changing. We wanted to kind of abstract that away to a level that we can kind of quickly put together mission files that can quickly define a mission that we're interested in analyzing, or that we can really put together the full timeline, official baseline timeline to run through. And so what we're going to be looking at, well, I'll get to that a little bit later. So the actual filter loop starts with checking our data stance, which is just, is it time to be tracked? Are we at the right spot in the NRHO to be tracked, or are we crewed? And if so, who are we being tracked by? And then there's a little bit of logic inside that handles handovers or not, if you want to disallow handovers. So if the data stance comes back and say that, yes, we are in an active data span, it will then simulate a tracking data measurement corresponding to who is active. If that measurement is taken, then it will be filtered, and that will update the estimated state and covariance. And then it's time to take our step through time to the next time step, and in which case we check our next step size against the event stance, which is kind of similarly to the data stance. We check the epoch and true anomaly against the list of upcoming events. And so if the next one is within a step size, we will scale down the step size and flag that event to be executed. Then we step the filter forward, execute any events that have been flagged, and then repeat until we arrive at an end epoch as defined by the command here. So when we say filter for 1 rev, it will calculate where the epoch is for 1 rev to get you back to the same true anomaly you were at, and then feed that as an input and execute this loop until you get there. So this simulation was run in a Monte Carlo on a representative 9 revolution missions. There was no docking. This is just to get to a steady state, orbit determination, filter solution, and then investigate how that solution is behaving. So we have 50 trials. That gives us 9 revolutions of 50 trials, 450 predictions. While we are crewed, we desaturate about every 6 hours, both while filtering and predicting. And so when we're predicting, we have cloned predictions from solutions so that we can put in these unique random desaturations on these predictions. So we end up with, while we're crewed, 4,500 Perilune predictions that we look at for each Monte Carlo. So the first, what were we looking at here? Okay. So this is just kind of going back over everything that I've said to this point, which is that we're looking at the Perilune performance, the prediction, the time needed to process the data, re-upload it, and so we're trying to capture the behavior in this time. So another thing to look at when you start to look at orbit determination, click on a filter, and start to process data is how well is this filter working. And one way to measure that quickly is the Mahalonobis Distance, which is a comparison of a solution against the covariance of that solution in the direction of that solution. So as an example here, we have a set of solutions that create a covariance by their population. And so we have 2 error vectors, A and B, that kind of point at 2 groups of solutions. And while A and B's magnitude is the same in space, the Mahalonobis number of these solutions would be greater than 1, as they are outside this covariance, and these would be less than 1. And so these solutions are possibly concerning if this is what's coming out of your filter. This would show that the filter has high confidence in an erroneous solution, whereas these solutions here, it has a lower confidence in this direction. And so these solutions are of less concern. This is considered healthy solutions, so to speak. And so the way we say that are outside or inside the covariance. And so the first analysis we look at is turning on and off error sources to see which one is the driver of errors at Perilune from predictions from the data cutoff to Perilune. So our error sources are the desaturation maneuvers, orbit maintenance maneuver execution errors, and the DSN range bias that we flip on and off here. These are random error sources. So that creates 8 combinations of error cases where we have these things flipped on and off in all the different manners until they're all flipped on, and that we would call our kind of baseline error modeling. So as we turn these error sources on, we look at how the filter is responding with its Mahalonobis distance numbers. So what we have plotted on the left and right are, with all of our errors off and on, the Mahalonobis numbers for position and velocity, whether we're predicting between active data tracking spans, which are highlighted in lighter colors. So position is in blue, velocity is in red. And so you can see with all of our errors turned off, everything, we start out with a high Mahalonobis number that gets down into a steady state. And then all of these numbers are nice and below, in the neighborhood of 1. However, when we turn all of our errors on, you can see every time that we have active data tracking, we get a spike in the Mahalonobis number in position that spikes up. And then in the times of prediction, it relaxes way back down as process noise is pumped into the covariance and it increases its volume, so to speak, so that the solution kind of sneaks back into the covariance and drops the Mahalonobis number much lower before it is then spiked back up by the tracking data pass. So what's happening there? The punchline is that the unobservable DSN range bias is moving the navigation position. So because it is unobservable, what we're seeing, because all of the motion is normal to the range direction in the NRHO, that the filter, what we call filter collapse, will collapse around an erroneous solution with a kind of pancake-shaped covariance, so that it's actually off and outside. The error is actually outside that covariance. And so when we go crewed, similar story. Now the entire time is highlighted, and the entire time has a very high, and you can see the filter struggling with these highly variable Mahalonobis numbers. So now we are looking at the actual results, actual errors at Perilune after a prediction from the past 2 data cutoff, and in each one of these columns are error cases, error model cases, where we have everything turned off, and then on this right side, everything turned on. And you can see as we flip things on one at a time in a kind of binary ticking fashion, anytime we turn on the random bias, our errors grow, and that shows us that the DSN range bias is the primary driver of prediction errors at Perilune. And so this is position on the left, velocity on the right. And so what we're looking at here are box wing plots or box whisker plots, where the notched line is our average, the box is our inner quartile region, our outer quartile region is the whiskers, and then some outliers plotted beyond 2.698 sigma. So when we go crewed, the story remains the same, and in fact gets even more stark, that any of these error model cases that have a random bias are the highest errors that we see. And in addition, going from uncrewed to crewed, just in general, we get higher errors from the additional errors from the predictions of the desaturations, or rather the perturbations of the desaturations. The other analysis we looked at that we'll be talking about today is the moving this pass, the number 2 pass around for uncrewed, or just moving our data cutoff backward in time or forward in time when we're crewed. And so when we're uncrewed, if we skip that pass entirely, we can expect, because we don't have any tracking data that rectifies the orbit maintenance execution errors, we can expect, under the modeling of the simulation, we can expect these position and velocity errors. But if that pass is 8 hours and ends with 16 hours or down to 0 hours of propagation to Perilune, we don't see very much of a difference, or it's pretty stable. So we say that there's a marginal prediction performance increase from shorter prediction time spans in that region. However, when we go crewed, because now we have the influx of those of the additional perturbations from the desaturations, we can see more of a change in our average and our quartile regions shrinking as we reduce the prediction time span closer to Perilune. And so we say we have a moderate performance increase from shorter prediction time spans while crewed. And so those are our conclusions. The range bias is our strongest driver. We call that filter collapse because that bias is unobservable. The crewed desaturations increase the mean and variance of errors at Perilune. And then just that the orbit maintenance maneuver execution errors, because of that pass two, assuming we do have that pass two, the predictions or accuracy at Perilune is not very sensitive to that. So that's about it for today. Wanted to talk about how we did it with FreeFlyer mostly. There was an additional analysis done here that's done in the backup slides, and I will not talk about today. Thank you very much.